Hi, I'm Abhijith Moni, a PhD student at De Montfort University, Leicester, United Kingdom. I'm here to talk about a reduced order model for computational fluid dynamic application. So the main objective is to build a reduced order model for a CFD system using Altair's Roam AI and to discuss the methodology involved in it and to use a set of training data to construct a Roam model that accommodates faster execution and accurate results. To predict an output of an unseen parameter using a trained row model and to compare the prediction against the CFD simulations. And the application used here is to predict pressure coefficient over airfoil surface. And the main reason for choosing CP because coefficient of pressure is integrated over the airfoil surfaces to get any aerodynamic coefficients. So I have both test and training dataset. My training dataset involved NACA 0012 and the mesh for the same can be seen in far and near views. And the mesh is consistent with training and test dataset. And the solver setup involves flow in VESET, transonic regime with a free stream condition and Mach number of about 0.85 and angle of attack 0 degrees and equation being Euler. To construct a training dataset, I use three different airfoils, and the data collected are XOC, YOC, and their corresponding pressure coefficient. And the data which is isolated for testing is NACA 0012. For data extraction, the ROM doesn't have to see all the parameters in the fluid domain. So the data of interest is isolated from the fluid domain, that being coefficient of pressure. And it is stacked up into a column of CSV file. We have three columns, XOC, YOC, and the corresponding coefficient of pressure. And it is a good practice to showcase the CFD results upfront before the row model construction. So these are the coefficient of pressure of three different airfoils used for the training phase, plotted against XOC coordinates. This is the architecture of the neural network I've used. So it has two input layers, one output layer, and three hidden layers with 50 neurons each in hidden layers. And these are the training parameters used for training the neural network. And the activation function I use is rectifier linear unit. And these are the learning rate, train split ratio, and epochs is about 500. And the module used is director Roam AI inside Altair's Activate. And so after the training, I get the training loss, and it was being plotted in here. And you can see the test loss being very low, and it is safe to say that the neural network is ready to make prediction. And to predict an unseen parameter of NACA 0012 test case of XOC coordinates and YOC coordinates is inputted inside a trained room, and the output of the pressure coefficient corresponding to the input is obtained. This is the CFD result for an unseen parameter of NACA 0012, which I'm trying to predict. This is the result comparison between the Roam AI prediction and CFD results. As you can see, there is a slight difference in Roam AI prediction and the CFD results. This is the main reason behind this is being in a transonic regime, which is very hard to make a prediction of, but the Roam AI did a pretty good job in doing the prediction here, and it is pretty much possible to use different data sets or more training samples to close down this gap. I'd like to conclude by emphasizing on the runtime. The Roam AI takes about less than 3 seconds to make a prediction here. And when you compare against CFD simulation, it takes about 140 seconds. This is a 2D case. Say, for example, if it's a 3D case, you might have to solve, if not billions, you have to solve millions of degrees of freedom. It will take more time. And it is also possible to use the Altair Roam AI to use it as a black box for these kind of simulation or use it as a surrogate model. These are some graphs in the appendix. I would like to extend my sincere thanks to Altair for running this contest, and would like to thank my university, my supervisors, Dr. Wigan Yao and Dr. Hussein for their continuous support. Thank you.